in the limit of 1 over, I prefer this form, it's easier to plug in, x minus 2, x minus 4, as x approaches 3 from the left. I don't know if this equals limit as x approaches 3 from the right. I know it will, because only for 2 and 4 it's not defined. So I know it's going to be the same, but let's write it. And I don't know if this equals f of 3. Yes, all of them have to be the same, because 3 is not 4 or 2. So 3 minus 2 is 1, but 3 minus 4 is negative 1. So this is negative 1. Same thing, there is no change, negative 1. So these two are equal, and of course there is no change, negative 1. So I will say yes. Why? Because the limit from the left of 3 equals the limit from the right of 3. They both exist, and they are the same. And also, they both equal the function value at 3. So therefore, the function is continuous. Any questions? Did we get the idea about continuity, or continuity at a point, or the definition of continuity at a point? Is that a yes? Is that a no? Is that a maybe? Anything? Anyone? Please say something, anything. Our next step is section 1.3. And in section 1.3, we're going to go back to average rate of change. There are no secrets. I just want to pick some problems with you. Average rate of change. And of course, the major issue here is the difference quotient. So we're going to look at that again. So we know what we're talking about when we talk about the average rate of change. Here is a function. Let's go back and review that. So here's a function. We want to determine the average rate of change between these 2 points. All we have to do is find the slope of this line. You don't even have to draw the line. I'm just explaining that it's the same with the slope of this line, of the secant line PQ. That's the average rate of change. Please remember it has 2 measurement units. Like, for example, miles per hour. Degrees per hour. That's another type of measurement unit, right? Degrees Fahrenheit per hour. What else? Can you give me other examples of measurement units that are ratios? Let's say feet per second squared. This is for the acceleration. This is the measurement unit of the acceleration, which is the rate of change of velocity with respect to time, and so on and so forth. So please remember the average rate of change, or a rate of change, has to have 2 measurement units, one coming from the numerator, one coming from the denominator. So I'm going to call this, so this is function f of x, and this is x1, and this is x2. Of course, we know that this is f of x1, and we know that this is f of x2. So what is the average rate between p and q? We've used this already a long time ago. F of x2 minus f of x1 over x2 minus x1. And then from here, I presented this at the beginning of the course because I can't wait till chapter 1 for many reasons. And then we looked at the difference quotient, which is the same thing, identical, just the notation is different. So this is p, and this is q, and this is f of x, and now this is x, and this is x plus a little bit, which really says to you that q is close here. I have to zoom in so I can explain what I'm doing, but they're close to each other. And this is, of course, f of x, And yes, you already told me when we looked at this. And this is a difference quotient. Rate of change between P and Q. So f of x plus h minus f of x divided by x plus h minus x, which we know the result is h. And you will see what happens when we finish this section. We will be putting together, I already said that some time ago, we will put together the limit operator with the difference quotient. And you'll see what happens when we put these two together, the limit operator with the difference quotient, and you'll see what happens. I wrote that some time ago for you. But now it's the time to talk about it in detail. So first, I would like us to experiment with some average rate of change. This is not new. We've done this before, either from applications or from numerical examples. I would like to work on some applications. If you don't want to choose, I will in a minute. And also life and physical sciences, applications of the rate of change, the average rate of change, average velocity, radar range, etc., etc. Okay, so would you like to start with an example that is a numerical example, or just go ahead to application? Say it again.
Okay.
Oh yes, I'm sorry. I'm sorry. Page 122 is the next section in line. Sorry. Page 122. So we want to, the first part on page 122, we have examples on finding the difference quotient for different functions. That's a very good example. We've done this before. This is not new. Nothing in this section is new, really. We've done everything. When we reviewed in R, we went through all this. Okay, so I think we should look at, let's say 16. You'll choose the next, please, if you'd like. So we have f of x equals x squared plus 4x minus 3. And we are asked to find the difference quotient. And you have to remember the difference quotient moving forward as being f of x plus h minus f of x divided by h. So keep in mind it's identical. It's just the notation is different. Instead of x1 and x2, I have x and x plus h. Everything is the same other than that. Okay, so this piece is known, clear. I just have to distribute -1 to all these three terms. This one is clear. There is nothing I can do to it. So the only thing that I don't have is f of x plus h. So I'm going to start by determining f of x plus h. Can anyone tell us how to write f of x plus h? Anyone? Well, the function is telling us that the independent variable has to be squared, which is this, and then plus 4 times the independent variable minus 3, so this is x plus h, everything squared, plus 4 times x plus h minus 3. And when I square x plus h, what do I get? How many terms?
3.
Yes, please, before you say anything, please. Okay, so then can anyone give us those 3 terms? So it's x squared plus 2xh plus h squared plus 4x plus 4h minus 3. So now I do have all this. And I'm ready to plug them in, replace everything piece by piece, and finish up and simplify the difference quotient. Anyone remembers the two conditions or two concepts? Every time we determine the difference quotient, those two have to happen. There are two things that have to happen here every time for every difference quotient. Anyone? All terms without h must go away. If more terms go away, that's even better. But all terms without h must go away. And the remaining terms, because all terms without h went away, the remaining terms have h in common. So I have to pull out the h. That will eventually simplify the h in the denominator. So we have a 2x, we have an h, and plus 4. And this is the final form of the difference quotient for this particular function. Okay, I don't know if you are into baseball. Let's look at problem 29 on page 124. I like baseball. Page 124. Let's read the problem. Oh, I'm sorry, I thought it was baseball. Oh, it is baseball. Okay, sorry. Yes, ticket prices, baseball ticket prices. Based on the data from such and such, the price of a ticket to a major league game can be approximated by P of x 0.06 x cubed minus 0.5 x squared plus 1.64 x plus 24.76. Let me know if I copied it correctly. As I said, sometimes the printout is a little blurry. Where x is the number of years after 2008. X, number of years after 2008. So I make myself a note. This means x equals 0 for 2008. And P of x is in dollars. So that's the price. Find P of 4, part A, P of 4, part B, P of 6, part C, P of 6 minus P of 4, and then D, find the average rate. Obviously, between 2012 and 2016. So we can put it in parentheses because 4 years after 2008 is 2012, and 6 years after that is 2014. Right. Okay, so we'll calculate that in a minute. Of course, we know the formula is P of 6 minus P of 4 over 6 minus 4. So P of 6 minus P of 4. I recommend the following steps in the calculator. I'm going to put this function up here, clear. So 0.06 x to the third power minus 0.5 x squared plus 1.64 x and plus 24.76. And of course I'm going to check and see what I entered. So 0.06 x cubed, that's correct, minus 0.5 x squared, that's correct, 1.64, that's correct, everything correct. So now I go to second and table, and I will plug in 4, and then I will plug in 6, and I will copy my numbers. So for 4, I got 27.16, and this is dollars. For 6, I got 29.56. Now when I subtract those, what do we get? And finally, I'm just going to divide this difference by 2. So what was the difference? 29.56. I'm lazy at this time. What do I get? I got 2.4. And this is dollars. So 2.4 divided by 2 is 1.2. Without a measurement unit, it means nothing. Can anyone tell us what is the measurement unit for the average rate of change? And what does it mean? We have to write the meaning as well. They're not asking to do that, but this is very important. That's what we need. What range of change, what rate of change does this represent? Okay, they do ask, sort of. And then I would like to, yes? I'm ready. Say it again.
The change in dollars.
So it has to have 2 measurement units. What is the measurement unit for the top?
Dollars.
Very good. What is the measurement unit for the bottom of the fraction, the denominator?
Years.
Good. So now let's write the meaning. The price goes up by $1.2 per year since 2012. I mean, from, I would say better. I will erase this. From 2012 to 2014. So the price of the ticket for the baseball games appears to be going up because the rate of change is positive. It's not decreasing, it's increasing. So the price is increasing by $1.2 per year from 2012 to 2014. Let's also look at the population change because it's a different function. So I like to look at that, and maybe home range or radar range, average velocity, any of that on the last page so we can continue. Any questions for me? Any questions? Anything?